Alright guys, here I am. This is David Reese. You can see me there. I actually am in Mexico and I won't be able to make it to class tonight. But I'm going to do my presentation via video. I'm going to send it to you guys. So here we go. We're dealing with intermolecular forces. Alright, we'll go next. Intermolecular forces. Okay, now a lot of times intermolecular forces are often confused with intramolecular forces. When dealing with intermolecular forces, the force or attraction is between different atoms or molecules, while intramolecular forces is an atomic bonding with a molecule or crystal, ionic, covalent, etc. Intermolecular forces are much weaker than intramolecular. Okay, let me say that again. Intermolecular forces are much weaker than intramolecular forces, and they affect the boiling and melting points of a substance. Alright, well, here are the intermolecular forces that we know about. Or, yeah, they're the most common. You got ion-dipole force, and that occurs between mixtures. You got dipole-dipole force, which is between a pure substance and a mixture. And then you have H bonding. Now, H bonding is part of the dipole-dipole force, yet it's very different on its own. It's its own individual bond. Then you have induced dipole. You have ion-induced dipole force, dipole-induced dipole, and induced dipole-induced dipole. And induced dipole is also known as London dispersion. Alright, we'll go to the next thing. First, we have our ion-dipole force. An ion-dipole force occurs between an ionic compound dissolved in a polar compound. Alright, now this number, 10 to 20 kilojoules per mole. That is the amount of energy required to completely disembowel, to break up the bond. An example of this is NaOH and H2O. And there's a little illustration there. You can't really tell. The resolution is not that great. Alright, next we have dipole-dipole force. And dipole-dipole force is an attraction of two polar molecules. It's a lot weaker than the ion-dipole force. It only takes 1 to 5 kilojoules per mole to break up this bond. An example of this is HCl. We'll be going to the next slide now. H bonding, dipole-dipole. Now H bonding is a special kind of dipole force. It's saying this because it deals with one element, hydrogen. Now, this happens between 3 other different elements, including hydrogen. It's a very special bond that only occurs between 3 different elements, which is fluorine, oxygen, and nitrogen. Another key thing about H bonding is that H bonds are the strongest of all intermolecular forces, and it needs 20 to 40 kilojoules per mole in order to break up the bond. Next, we have induced dipole. And basically an atom or molecule that is originally has no polarity and yet can develop a polarity from an outside force. So to give you an example of this, I know the definition doesn't really say much, but the best definition of this is this picture here. You can't really tell, but on the right hand side there's a yellow wall with its positively charged ions towards the left and its negatively charged ions to the right. And to the wall you have a balloon that is negatively charged through what we call static electricity. Now what happens with that is when you grab a balloon and you rub it against your hair, it creates static electricity. And when you put it against the wall, it rearranges the different ions there, and it attracts the positive ions, and there's that little bond. And that's why after rubbing it on your head, you can place it on a wall and almost leave it there, and it'll stay there. So that is induced dipole. Next, you have induced dipole force. Ion-induced dipole force, excuse me. And basically, an ion-induced dipole force is when an ion will either attract or repel electrons in a nonpolar molecule or atom. Also very weak, only takes 1 to 3 kilojoules per mole to break the bond. And there's an example of that. And here's a demonstration between cesium and fluorine there in the middle. As you can see, fluorine is negatively charged, and those blue arrows that are facing towards cesium is positive charge, so it pushes away the negative and draws the positive. Alright, so next we have dipole-induced dipole force, and this force occurs between polar and nonpolar compounds. Probably one of the weakest forces, as it only takes half, between 0.05 and 2 kilojoules per mole. An example between this is H2O and iodine. Alright, we'll go to the next one. Finally, our last subject is London dispersion. Now this occurs between two nonpolar compounds or atoms. It is also known as the weakest of all intermolecular forces and is caused by distortions of the electron cloud. Now basically when there is a depiction of an atom and its valence electrons and the different shells, they're drawn in circles. However, even though this is great for the illustration purpose, it isn't exactly true, where in fact the electrons are in what a cloud, and the exact location of an electron at any given time cannot be proven. It's not on a set course. It's just in this crowd, in this given area around the atom. Now that's the electron cloud. So when it says that the force is caused by distortion in the electron cloud, just imagine that cloud being moved. Alright, so we go to the next one. Large molecules or atoms have a greater LD because it is easier to distort electron cloud. And basically, the heavier the molar mass is of a molecule or an atom, the greater force of London dispersion there will be. And the greater the mass, the higher the melting or boiling point. An example of this is highest boiling point to lowest boiling point. And I'll tell you right there. You got F2, Cl2, Br2, and I2. Now they're all in the same column, but as you can see, it goes up. Highest boiling point F2 to Cl2 to Br2 to I2. F2 has the greatest mass, greatest molar mass, followed by Cl2, Br2, and then I2. And next we have a problem. Just one problem, just to make it easy for you guys. Arrange the following from the lowest boiling point to the highest boiling point. Also, name the intermolecular bonds that determine the boiling point. The subject and matter is NaCl, also known as table salt, Br2, H2O, also known as water, and He, helium. So you got salts, bromine, water, and helium. I'll give you a moment to work that out. I'll give you about 20 seconds starting now. Okay, well there was about 20 seconds. Now let's go to the answers. And here's your answer. From the lowest boiling point to the highest, you have helium, bromine, water, and then salt. For HE, the greatest force being used is London dispersion. Now HE has a very low molar mass, which would make the distortion in its cloud very hard, or harder than it would have been if it was a greater molecule. You got Br2, bromine next. Bromine has a higher molar mass than He. Now both of the forces being used is London dispersion. And so we got that, and so because of that, Br2 has a higher boiling point. Then you got H2O. Now this is a special case with hydrogen bonding. Basically, it's the strongest force there. But then we got NaCl. And this is kind of a trick question because it doesn't deal with intermolecular forces. It's an intramolecular force in its ionic bond. Next slide. Alright, here's a relevance to microbiology statement that I've made. And I'm going to read it verbatim. In order to graduate with a BS in microbiology, many chemistry-related courses are required. These courses include general chemistry, organic chemistry, and biochemistry. The subject of intermolecular forces would fall under general chemistry, and for there to be improvement on the next level of biochemistry and organic chemistry, mastery of general chemistry is needed. Thank you. This was David Rios for my part in my final presentation of, well, there it was.